Last time actually, Wang Peng followed about presented the optimization. Optimization is here plays two roles. One is that we know later when we train neural networks, we need optimizations. So that's the purpose. Second, as we'll see, right? Probably we have suggested, hinted before. Optimization actually plays a second role here. Probably most people don't know. Right? Optimization itself actually is what the neural network itself is. The architecture of neural network is actually trying to realize certain types of optimization to serve certain purpose, to optimize certain objective. That's what we'll see that repeatedly for the rest of the course. Right? That's how you understand neural networks. The neural network itself is an optimization algorithm. Right? When we train the neural network, we're improving that optimization algorithm, making the operator, iterations, layers as operators better and better. Right? So that's the way to explain it. So Tom kind of went through, right? As you can see, almost every book I wrote, right, there's always an appendix about optimization, 3D division, high-dimensional geometry, and also deep learning, right? So optimization is everything. In fact, computing, where we call school of computing, right? Computing is optimization. Optimization is computing. All right? Everything that can be computed, in fact, most of the things, as we see, majority of the problem in the world, right? We don't have closed form. We always resort to numerical solutions. Hence, it's computing. That's what a computer is. It's trying to realize what is computable. In fact, most of what's computable is actually trying to realize optimization algorithms. As simple as solving linear equations. Okay? Resort to PCA, SVD. Okay? Resort to power distribution, optimization algorithms, solve that. So almost every single meaningful, useful, practical computing problem that deserve computers to realize is actually optimization, including search algorithm, right? Learning optimization, sorting algorithm, right? Including reinforcement learning, optimal control, including all algorithms learned last time, right? So including, that's why even Newton, Gauss, they're probably more remembered. Both of them are remembered more for the invention of optimization algorithm, right? Newton iteration, Gauss citadel descent algorithm, Gauss gradient descent algorithm, right? Understand? That's how important it is. Right. Optimization is what separates, what connects abstract mathematical concepts to what's real, what's implementable, what's computable. Right? So this is how important it is. Never underestimated the optimization. Right. So also Slay side, please TA, they're TA, right? So please take attendance record from now. So hence, of course, when we talk about the optimization, right? Usually optimization, we're optimizing on the domain. Domain are, there are different restrictions. I think Tom went through that. And also the object function. How difficult or how easy to optimize optimization algorithms depends on the domain and also constraints, which area the function is defined, right? This is which area the domain is defined. That's usually a constraint, right? X is larger, the solution you search is restricted to a certain area. Second, we optimize the function defined on this area, right? And also how easy to optimize also depends on both. What the domain looks like, and also what the function looks like, right? The easier the function, benign the function, the nicer the function, the better. Right? So of course the easiest type of function is the convex function. Why? Intuitively, a convex function usually only have one global minimum, right? Or concave function, one global maximum. So it's easy, conceptually it's easy to optimize, which is indeed the case. Most algorithms that if you apply it to convex functions, you can expect first the algorithm converge, to the global minima. Second, the convergence rate usually is much better guarantee, converge faster, right? That's the ballpark, right? And hence, we normally try to solve the problem, try to minimize some function against some variable x, and also subject to some constraints, right? This is the most natural family of problems. Constraint optimization. Of course, you probably learned, right, from using Lagrange multiplier, you can convert a constraint optimization to an unconstrained one, right? So you can actually see that if you know the history of optimization, almost all famous mathematicians, right? I told you what's the difference between a great mathematician and a mediocre one, right? Average mathematician. The great mathematician knows how to compute, right? If you know reinforced learning this year, right? Reinforced learning 今年得的图灵奖，对不对？ But reinforced learning has been, in fact, it's been reinvented so many times, right? In fact, 这两个得图灵奖的 invented nothing, okay? Every old idea has been invented, right? 你知道那个 reinforced learning solved the problem is called Euler, Lagrange, Bellman, Euler, Lagrange, Hamiltonian, Jacobi, Bellman-Ford equations， 知道吗？从 Euler 这里面，欧拉这里发明到 Lagrange， 对吧 ？Lagrange transformation， 知道 Lagrange transformation 吗？对吧？对吧？到 Hamiltonian、Jacobi 听说过吧？学数学的都有，对吧？Bellman-Ford， Bellman 对吧？动态规划 ，Ford 啊，所以 this is just reinvention, guys. There are not that many great ideas, actually, new ideas. It's just reinvention of it. Probably reinventing a new, better context. 就是重新发明在新的 context 的发明，当然也是有意义的啊。So, and this kind of problem, then of course, in general, right? For example, many problems we deal with, even with constraints, for example, right? Constraint optimization, very natural one. We try to do basis pursuit, right? You have to solve linear equations. We try to solve y equal to ax. Try to solve for x given y and a, right? Especially when we want x to be sparse. This is already looks simple, but this is a constraint optimization. This is a convex function. This is looks benign. 看起来很简单，实际上也很难了。Right? Because this is not smooth. Turns out this is constraint optimization. You can use Lagrange multiplier, convert to this called lasso. OK? 这叫sparse regression problem 啊，是大家今天见到的，对不对 ？This square fitting regress y with regressor a using a sparse, uses just select sparse number of columns of a to representing y. Right? 看起来很简单，这个问题实际上这个问题已经是NP hard 的问题。But turns out this actually can solve by convex optimization, right? So very often, right? This convex 还好一点, right? It's easy, right? Convex optimization is at least we think it's benign, so on. But normally we hate non-convex optimization. This is always very scary, right? Non-convex optimization is very scary, right? At least intuitively, because it looks like this, right? Either there is some area very flat. If you are in those flat regions, you don't know which direction to go. Right? Locally, don't know which direction to go, to descend, to reduce the value. Also here, right, you can easily get stuck with some local minima, right? So gradient descent can easily get stuck with some local minima. You can never get solved, right? So normally, non-convex optimization usually are very hard, right? In general, it's very difficult problem to optimize to find the global minima. For most non-convex optimization, many of them are even NP hard to find the local minima. Okay? Now, find the stable local minima sometimes can be a bit hard. Okay? So that's why people usually don't like non-convex optimization. But it turns out, suddenly in the past 10 years, we do this all the time. Right? So what's the mystery? Right? Train a neural network. Those functions are highly nonlinear. Right? But we're doing that, right? So it turns out actually we'll see later, right? Most of non-convex optimization we're dealing with actually has a very benign landscape. Right? So how do we do optimization? Of course, this actually traces back to Cauchy, right? Cauchy. First, let's just do爬山的绘法, right? If you want to get it to the peak, right? Or descend, right? Just follow the gradient. 上坡下坡，对不对？ Then just follow the gradient until you reach the bottom. Right? This is a very simple idea invented by Cauchy. 听说过这个名字吧？哎，你想想，有名的数学家都是在干什么？ Right? They knows how to compute. Right? So how to compute this? Actually, we just descend with a small step. And by step, compute the gradient and descend in certain direction. Of course, there's a lot of issues. Okay? Depends on landscape. If you take a very slow step, it takes a long time. Right? 小脚旅人走路啊, if you take a very slow step, it takes a long time. Or if you take a very large step, you isolate, right? You jump from hill to hill, right? So you actually can never converge. So take the right steps is very important, right? So basically just take steps is not, right? How to take the right step size is actually very important. And hence, this is how to take the right steps, right? So if you take a very large step, you can overshoot. So turns out you can say, how do we decide the steps then? So ideal optimization is that you don't have the global information of the function. You only have local information. You only know the gradient, probably only up to first or second order to compute the shape. Sometimes you cannot afford to compute the second order. Okay? In order to compute the second order of function, you need to take the second order derivative, right? That's Hessian of the function. When the variables is large, it's very, very expensive, right? But regardless, almost all computing algorithms, all optimization algorithms relies on approximating the local shape of the function, right? Either as a linear function or some kind of quadratic function. If you get to the second order information, you can approximate, right? With the so either, for example, if you want to optimize this black curve, right? You can usually the algorithm. There are two ways to approximate. One is find the upper bound of the function, like the blue curve. Right? One is find a different upper bound, right? So if you find a better upper bound, you can see the red curve is the better upper bound. If you find a very conservative upper bound, you go to the bottom of the blue curve. You take a very small step, right? But if you find a very good approximation, you can take a very boldly, take a large step, but still remains on top of the function, right? You never overshoot, right? So there's always guarantee such upper bound. If you go to the upper bound and the minimum of upper bound, you always never overshoot. That's actually the idea. So the design of the gradient descent is always try to approximate the local shape, right? So that's why gradient descent is very different from gradient descent. 不是一阶算法就跟一阶算法是一样的 ，OK？ They can the speed, the efficiency can differ by 4 or 5 order of magnitude. If you the better one versus the worst one, okay? If you design very well, that's why there's 30 years of study of gradient descent, right? Actually 300 years, right? 300 years. How to condition, how to approximate the shape, conjugate gradient descent, preconditioning, all the training neural networks. I can tell you, right, including whatever you heard, lateral gradient, solving reinforced learning, right, lateral policy descent, all the things, add-ons, everything you heard these days is just different ways to approximate the functions properly. Okay, different ingredients, right? How to decide the shape, and of course sometimes we're dealing with function which may not be smooth. For example, L1 more, right? Absolute value. It's a convex function, but it's not everywhere smooth. So what do? You use a subgradient, right? You use a proximal gradient. This is a generalization of subgradient. 对吧？搞了 that your subgradient here is actually any line below that point. Right? So the generalization, you can see if it's a smooth curve, it's precisely tangent to that curve, right? So if it's a subgradient, it can be, if it's not smooth, could be any lines going through that point below this curve. Okay? So it's generalization. Turns out you can choose, from an optimization point of view, you can choose whichever one of them. Again, choose a better one, converge faster. Choose the worst one, converge slower. But you can conceptually just replace gradient with a subgradient. Okay, that works. So you can actually come up with a so-called proximal gradient descent, right? If there's a non-smooth part of function, especially the subgradient can be computed in closed form, you can do the proximal gradient, right? That only applies to certain g, right? Not every g. Some g, the proximal gradient, this proximal operator can be computed, such as L1. There's a family of functions, this g can be computed, so that's actually makes it very efficient. The convergence rate is almost as fast as the convex part, smooth part case. Right. So, for example, minimizing one more, naturally corresponding to this kind of soft threshold. 如果你去优化 optimize this kind of function, naturally the solution to this kind of function is do a soft threshold. If you also want the x to be positive, during neural networking, we want the weights to be positive. We do what? Redo, right? So look at this. So if you do make sure x is positive, this soft threshold looks just like a redo. But it turns out actually the redo is exactly sparsifying the coefficient or the features for you. So this is called the proximal gradient. So it applies to any function. Right? Even the gradient is even the places where it is not smooth, you can take the subgradient to optimization. So you see that, and you see, the algorithm, you can now, once you do this, the rest is just calculus. How to compute the gradient, right? Subgradient of this object function. Right? There's a quadratic, the traditional least square one. Of course, there's this L1 regularizar. Make sure x is sparse. Right? It's the absolute value of L1. 它的绝对值的和，对不对？ Then the operator turns out that the gradient, then you do the gradient descent. Every step, compute the gradient, take a step, length 1 over lambda. So the lambda is 1 over L. L is the constant. It's called the Lipschitz constant of the function. G is to determine. And then take soft threshold. Right? Just keep reiterating this. Okay? If you look at this, right, it's a linear operator on x, residual term. Right, this is residual, this is a constant term, skip connection, plus one linear operation. What this looks like? It looks exactly like a ResNet. In fact, ResNet 应该正确的说法是 ResNet looks like this. Okay? It's trying to do this kind of sparsifying gradient descent. Right? Network is actually emulating this kind of algorithm. Right? This algorithm called iterative soft thresholding, right? This is obvious, right? Take iteration and do soft thresholding. Iteratively taking soft thresholding, right? That's the name of the algorithm. Right. So this looks like a neural network. Right. In fact, we're now the first only one to recognize this, right? 2010年啊。在 neural network 热之前，你知道量量空在干什么？也系数表达。OK， 做 dictionary learning. It was precisely working on dictionary learning, working on spatial representation. Learn the dictionary A. He actually recognized this is exactly neural network. OK。所以你学点数学好啊。就不用自己瞎猜，对吧 ？A lot of things like great ideas already in the literature in history has already been invented there. You only have to make the connection, right? So that's how you learn principle. You don't have to. 不像凯明啊，数学不好，那就只能试了40几种 architecture， 最后发现 ResNet works. In the end, looks like this, right? That's another way, practicing in trial and error, no problem. 所以对吧？ So if you don't have intelligence, replace that with diligence. OK？ 知道吗？对，最怕是，对吧？又没有 intelligence， 又没有 diligence， 对吧？人不聪明还懒啊，这个没办法啊，我们就不要可久了啊。This is actually a very good comparison. OK， so you know this, you should guess what the neural network looks like. Make it very stable. See, almost all. I see one great. See, in the beginning, right? when you try to remember, when you train neural network, it's very, very unstable, right? Remember, this a long time, how do we do normalization, we do learning rate, there's a lot of trial and error. There's a lot of optimization. They tell you precisely how to choose this architecture, how to choose this gradient, right? How to do the normalization so that the segments converge. This the 200 years of study, precisely study, tells you when the system is stable, when the optimization converges to local minima. Okay? There's a 200 years of great ideas. So you don't want to throw that away or try to reinvent all that, right? Spend billions of dollars trying to reinvent all the architectures. Okay? That works, but it's a detour. Okay? It's not necessary. And of course, another idea. This is one of the greatest ideas, right? So, of course, people do gradient descent, right? So the gradient descent is only use the information at the previous location xk, right? Only the location currently I decided which way to go, how far I go, 对吧？爬坡的时候，下坡，对吧？ If you descend, starting from this very step, I decided where to go. Okay. But of course, if you think about it, maybe where I come from give me some information, 对不对？对，我上一步在哪？ My previous step may give me, so I go from xk minus 1 to xk, maybe that direction give me some information, 对吧？所以我从哪儿来的，可以告诉我将来该怎么走，对不对？ So maybe this information gave me some direction too. 明白吗？ Right, I carry a little bit of momentum. 你下山的时候，对吧？前一步，我前面这一步走的是这个方向，我不能直接做个急转弯吧，对不对？ So maybe this gave me the gradient at this step. The previous step gave me this direction, right? Till I reach that point, then now it tells me this direction. So I have to make a turn there, right? Maybe I should go between the two. That's it, right? That's a simple idea, right? So if you think about this, if you just think about this, right? This is from Lula, right? Polya, and Polya 这个，这是两个非常有名的有数学家 ，right？ 写那个 Polya 的那个 Lula 他们俩 work。Do you know why did they do this? Polya 是这个非常有名的数学家，写过这个十分析的分析极其有名的最有名的应用数学家之一one of the most famous。 Polya 也说过一句很有名的话 ，has said something very very interesting, right? The idea works once is the trick. If it works twice, will become a method. 数学里面Did you know the background why they invented this algorithm? They're solving obviously they're solving some optimization algorithm, right? Some optimization problem. You know what the optimization problem they're trying to solve? Look at the time. 1960年doing mathematical physics, right? Publishing in Russia, by the way. USSR, right? 苏联人很厉害基本上所有的好的算法，说最早的，对吧？牛顿的，后来基本上优化这样子都是欧洲人好的优化算法都是基本上是欧洲人搞的。Why？ 我们这儿想一想Why？ almost all the clever ideas for optimization is from Russia. Why? 他们没有计算机用手算他们做这个事是算氢弹第三氢弹的时候，要解一些优化算法，优化问题。Hydrogen bomb, they invented this. 这个算法就是 Adam 的前身，现在我们训练 neural network 就是 Adam 嘛，对不对？Appendix 里面有对，所以 Adam 还是一个很粗糙的版本就不说了这个说的都是一堆血泪史这数学没学好的，后来都忘了，重新发明东西都很结结巴巴的。Anyway, so this is actually turns out that this simple idea can significantly speed up the gradient descent algorithm. Okay, very very fast. So the problem here is that, keep in mind, remember we try to approximate this gradient, right? We try to approximate the local shape, guys. right? Which are not possible. But we only can compute the gradient. We cannot compute the Hessian. It's very expensive. Forget about it. One variable is okay. If you have billions of variables, forget about it. Okay? That's why there's nobody implementing Newton algorithm, right? Because that requires patient computation, the second order. Also, you not only compute it, that's already quadratic. And also you have to invert it, that's cubic. Okay? 好比 sixth order， 而且还是第一次矩阵可是 cubic， 如果是全 four matrix 的话，它是60号，那受不了。Okay? Okay, so you can only compute the first order method, right? But you still want to use the history, right, where you come from, hopefully to approximate that trend, right? You want to use as much as the second order information, from the first order information to approximate the second order. So hence, using a little bit of history has a little bit of flavor of that. Right? I know what my previous gradient is. I use the difference of two gradients to kind of approximate that second order information. Right? 虽然很粗糙，但是总比没有好。Right? It's better than nothing. Okay? So that's why this actually speed up. This is already implicitly using the second order information. Right? 当然我们还讲还有另外一个 trick 可以用，可能上次课王鹏老师已经讲到了。Right? There's another trick 加噪声啊 ，that's a different story. So, but this actually works very, very well, including design nuclear bomb. Right? But for many years, people don't know if this is optimal. Because for gradient descent, if you use the only first order method, people know the convergence rate is 1 over k. But people also know from mathematical analysis, people see in theory, using first order information, gradient, in theory, you actually can have the convergence rate can be 1 over k squared. If you use the first order information, including the history. People actually know that for a long time. But the question is, do I only use the history in the k minus 1, or do I have to use k minus 2, k minus 3, k minus the whole sequence? Or how? Right? Is this already enough? Or do I have to use x minus 2? If you use too long history, also that becomes very clumsy, right? I have a lot of memory to memorize more things. So you pay a very heavy price. So for a long time, see, this is 1946, 64. And this is not answered until like 20 years later, right? Although people have been using this for 20 years, design nuclear bombs, design all the things, right? Solving very high-dimensional optimization problem, and using the momentum method, which is exactly as I understood, right? So, I mean, this is another genius. It's Lestrov, 对吧？说吧，都是 Russia 所以如果优化呀，优化啊，那个我觉得优化就大概优化 is almost all right. Maybe optimization, right? It's about 250 years of history since Cauchy, right? Cauchy. Then there's only probably, in my opinion, okay, there's probably only 5 names to remember: Cauchy, Newton, Gauss, Polyak, Lestrov. That's it. All the key ideas are invented by these 5 people. Nothing else. Nobody else should have any other credit. Okay? 5 people. All right. Gauss, Gauss invented the gradient descent, right? Newton invented the Newton method, second order, or fixed point algorithm, right? Contracting method. Gauss invented what? Gauss citadel descent, that's citadel descent, that's actually parallel, okay? Block optimization. 是我们现在并行优化 ，federal learning， 全部都是，对吧？现在有很多 fascinating， right? Different names, parallel. When your optimization function has parallel architecture. That's even okay. Started. Then momentum algorithm. Audience. You had an idea using history. Very popular. Everything just exactly that. And then what is the Lestrov did? Lestrov proved it. Right? So for a long time we don't know how long history should use, right? Should you use k minus 2, minus 3, minus 4 for whole history? The theory is theory, practice is different, right? So it turns out he actually proved that this actually is optimal. You only need xk minus 2 to reach the theoretically optimal convergence rate, 1 over k squared 2. Not only that, right? He told people how to do it. How to do this, right? So he even gave the recipe for the coefficient, even the step size, right? You don't decide nothing. So the idea is that very straight, right? So this is one of the greatest paper. He wrote in 1953, right? Saw like many years history. People don't know this. And the paper is only 5 pages. Everybody, you guys should be able to use this college math. Right? It's actually wrote in English. 1983. Should go read it. Like in my book, in the previous book, there's a proof. You actually can check it out, right? So the idea is, so that's why sometimes we think, first of all, we think, by the way, there are 2 lessons in history. Right? One, true innovation is very difficult. Okay? 不是那么容易的 because there's so many smart people. 比你还努力 okay? Who works harder than you, smarter than you, have solved the same problem. It's a very hard business. Okay? Truly be able to invent something new. So don't take that for granted. 别看我们现在就是放在每天很棒，对吧？没这个新东西。这 conceptual idea okay, just found that it's very difficult. Second, sometimes the greatest idea is just in front of you, just nobody pay attention to it. 有时候真正伟大的发现又很简单 ，because it's something is on everybody's blind spot. 就跟一样啊，牛人network 30年冷得一塌糊涂，对。对，现在都伺候诸葛亮啊，钱都造对吧？好什么都写了，真的吗？ Are you sure? No, we're not. Right? So this guy is amazing, right? So look at really said, what's wrong, right? So for about 200 years, everybody really said, anything wrong with this? Well, I mean, I'm here, right? 下坡嘛，对不对？这个这个地方的哪个地方最陡，往那儿走嘛 ，right? Nothing wrong with this, 对不对？ Well, this guy says differently, right? Over here, right? He said, see, I come from there, right? K minus 1. So I'm here, and that's K. He said, I come from there, right? So why not I follow the same direction, move a little bit first. Then I compute the gradient at the new place. 你看，他把这个往哪儿睡起一下啊？原来都是嘛，我的这个 compute gradient 以后，我看我从哪儿来的，这个原来是这么走的，对不对？现在的 gradient 在这儿，对不对？对吧？然后中间取个平均嘛，就是 nothing wrong with this, right？ 所以所有的聪明人都这是没有什么错的嘛，对不对？不可能错嘛。对。然后呢，这哥们儿来一个，哎，我先走一步，然后走到新的位置再算gradient。再沿着这个新的，我先走到，沿着原来方向 move one point, takes 4 steps, then carry the momentum, goes a little bit, and then in the new place, I do a gradient descent. 你看 just switch order. It's a huge difference, turns out, right? Then there's become there's thousands of papers written about this after this. Right? First off, you actually can prove with the recipe, even the alpha beta precisely given to you. You don't get to decide anything. This gives you the fastest acceleration. This immediately can improve the gradient descent, right? Immediately 1 over k squared. This is immediately cut the optimization from used to take about thousands of iteration to a few hundred. Okay? Magnitude, couple magnitude speed up. 都可以给大家对的。所以现在的 Adam 还用这个 老的 idea，OK？ 就你们可以想象啊，这个用这些 acceleration， 后来就 there's a family of acceleration algorithm， right？ Also, what's wrong with this picture？ 流动算法就在做这个事情，对不对？从流动开始，流动 is tell us we compute the action, we approximate this point with a quadratic， 对不对 ？Best quadratic, then I know exactly where to go. Go to the bottom. That's exactly Newton algorithm. We approximate this with a quadratic function. That, right? We find the upper bound of the function. That's how we prove the convergence right away. Right? Guarantee the convergence, right? This is all the things, all of the essentially learn upper bound of that function. You see? So we always find a using quadratic function to upper bound of the original function. You minimize this quadratic function. It's very easy to optimize. Find the median, right? 这个想法也是大家玩了200年，哎 ，What's wrong with this? Nothing wrong, right? 因为有时候说的那个 invention 非常难，但是有时候很简单啊。那 Nastro 就是这么想，但根据证明 Nastro 的思想不是这样的，要去证明啊，你就要加速嘛。Upper bound is very conservative, right? Upper bound they always make sure if I descend here, I will never. This is always since this value is below this, so I always reach a point that the function, the original function, the value will be lower than where I started. Okay, that's what upper bound guarantee, but it's very conservative. What about lower bound? What if about I find the function find the lower bound? Lower bound 就很 slippery, right? 就很滑，对不对 ？Upper bound 是很陡嘛，对吧 ？Upper bound I always What about the lower bound? If I find the lower bound of function, right? The problem is that if I go too far, I could go here, actually jump over there. So the stack can be very far. 是不是 That's the idea. 200年大家没有用过 lower bound 去 design algorithm。就跟200年大家没有去想过把这个 gradient 和 steps 分开。That's why we think that this is a stroke of genius. OK， 有时候这个你就在你的眼前，就是大家都不做的事儿，大家都有非常 convincing 理由不去做，其他人傻瓜嘛，对不对？对吧 ？Obviously bored。但是大家真正 dismissing 的 idea 并不是很 convincing， 并没有非常真正的 rigorous reason to dismiss. Remember we mentioned something last time, right? The dictionary. We dismiss bilinear is very difficult to solve. Even if you can solve bilinear, the data complexity is exponential, right? Those arguments, those sounds very compelling, right? Very convincing. But turns out actually they're not rigorous. To dismiss something actually is very, very powerful. The same here. Well, of course, since Newton we're doing upper bound. So must be nothing wrong with it. Since Newton, we have been doing the gradient first and then taking momentum. Right? Turns out we just flip this. And this is actually precisely the idea behind this precisely using lower bound to accelerate the function. Because lower bound allows you to explore the landscape in a different way. Yes, it's very slippery, can be dangerous. 对吧？对吧？什么？中国有句话叫什么？富贵险中求，对吧？就是因为 dangerous the routes, but also there might be reward, right? You can go faster, right? It's not very conservative. As long as you control the steps, okay? 走险路，但是呢 calculated risk, okay? Calculated risk. 所以看看，一下子是 open the floodgate. Almost all the modern algorithms are designed acceleration within this ideas, right? Mirror descent, whatever, people 对吧？而且这些 idea 还没用到设计神经网络呢 ，right？ 还没开始呢，that's all. right? Also, another one is, of course, gradient descent. Sometimes you cannot compute the gradient, right? It was that, right? So sometimes you only have samples, and you cannot compute it very accurately. Actually, you stochastic gradient descent, you can batch to compute to approximate the gradient, right? This is actually called a stochastic gradient descent algorithm. Basically, it's trying to approximate gradient in some way. Of course, the gradient is not very accurate. That's why, so they introduce kind of the noise. Right. I'll try to skip this. I hope Adam is kind of trying to do this to approximate those gradient in the sort of stochastic best way. Right. This is essentially the momentum algorithm, by the way. Right. So now, on the conceptual point is that. So I don't really is that. Right. See, of course, if I commit it to the greedy, the most greedy direction, it's okay, right? I'm descending it, but I could also get stuck with something, right? So, but if I approximate the gradient, I add some noise to it, give myself some degree of freedom, 对吧？这个大概这个方向，那我跟你们学一学啊，绕一绕啊，这样可以想。This actually adds a little bit noise to it. It's actually very, very useful. Right. What is it? Remember, guys, the gradient is very deterministic. It only tells you what at this point, giving you a very deterministic direction, right? It doesn't only depend on this point, but does not tell you what's around you, right? Doesn't explore what the slightly bigger shape of the landscape looks like, right? So see the second order derivative give you a better, but I cannot compute it, it's too expensive. Hence, maybe I add a little bit noise so I can explore the region a little bit, right? So that's exactly the idea. So I add some noise, turns out, very amazingly, right? You can actually derive this is the, right? So if I add noise to my gradient, this is actually associated with actually equivalent to compute duplication mathematically. Basically, it's almost you use add a little noise, allows you to have a little exploration. That actually jumps around a little bit, allows you, is always equivalent to calculate a little bit about the bigger area, the shape of the object function. So give you a better decision where to descend, or to escape local minima. So I think the idea is that behind, this is called the Monte Carlo, or simulated annealing. 对吧？模拟退火方法，所以这概念，名字取得很好，实际上这是很简单的 ，add a little noise， 对吧？对。Who has this idea? By the way, 你看这个很large. The original idea is the Laplace 的想法 ，OK？ 每一个 famous 的 mathematician 啊，都是优化情况。 都在做 compute. This is actually from Laplace. Actually, Laplace actually proved this. If you do adding a little bit noise, Laplace actually proved something very, very amazing. If you add a small noise, if you reduce the noise to smaller, from some large noise to smaller, right? You always converge to the global minima of any non-convex smooth function. Well, it's a little bit expensive. It takes a long time. But if you can gradually reduce the noise from large to small, you can actually prove you always converge to the ground. This is actually in my previous book, in the pad. The proof is half a page. Very simple calculus. It's called Laplace method, small noise method. People know this a long time ago, right? In fact, all the stochastic gradient descent is actually sort of a approximate version of this. Okay? Try to implement practical implementation of noisy gradient descent. Okay? So a big lesson we learned that in the past 10 years is that remember the previous picture about non-convex civilization, right? Very rare shapes and so on. But first of all, that never happens. So almost one bigger lesson we learned in optimization in the past 10 years in practice, almost all the naturally arise optimization problem 就说不是人假想、臆想的 object function. As long as you arrive in physics, in geometry, in the natural problem with good structure, like AlphaGo, right? With rules, regular function. Those object functions, turns out they're not that scary. They have very good structure, right? They have very good symmetry, right? The global minima, local minima are highly regular. And they don't have flat regions. The saddle points are always rideable. 就跟滑梯一样, you'll never get stuck on those critical points. It's very easy to escape with a little bit of randomness, a little bit of noise. You can always reach to one of those stable local point. And even those local minima has very good properties. 明白吗? So hence, this is a very bitter lesson. Turns out that's why gradient descent, this completely changed people's opinion about the non-convex polarization. Right. So as a result, one of the John Wright, my former student, one of his PhD students wrote his thesis. It's called "Why, When Non-Convex Polarization Optimization is Not Scary." Right. This entire thesis about a few years ago. Completely changed people's opinion, understanding about non-convex polarization. See, this is a very interesting discovery process. But what is the name? This is what they think that will change people's mind. Actually, in fact, even the previous high-dimensional geometry and statistical optimization completely changed about the 200 years of orthodox opinion about optimization. Okay? Now you have seen quite a few things, right? A lot of things people think, oh, it's impossible. Oh, very hard. Or NP hard. Oh, don't even bother. Right? Or non-convex polarization is difficult. Or gradient descent has to be done this way. Right? Because this has been done in 200 years. Right? Newton told us so. Right? Gauss told us so. Right? Well, there's always some Russian. Well, maybe we don't disagree. Right? We want to be discreet. Right? 所以同学们，你们想想啊，有时候我就说，一直告诉大家，真正的 innovation 是很难，但有时候伟大的 innovation 可能也很简单，就是所有人的 blind spots。OK， 哪怕世界上最聪明的、最了不起数学家 ，they always have blind spots. Right? So you do have the guts, you have the way to look at it. Everybody use upper bound, right? Well, let's trust it. I'm going to use lower bound. Right? Everybody compute the gradient first. I'm going to compute later, right? What happens if I switch? Right? That's actually a very simple idea, but make a huge difference in history. Now, how is related to optimization? First, in my lecture before, right, we talked about when the structure, when we try to learn the data structure, right? The data lies on the dimension subspace. We actually know the solution, right? It's PCA, right? We project the data into the lower dimension and we decode it, right? To solve this matrix factorization problem, the rank matrix factorization problem, computing the eigenvalue, eigenvectors, and so on, right? We do this, and we use high iteration, right? Compute very efficiently, compute the base, and we can do the projection, and then we can denoise, right? Essentially, we can denoise X into the subspace. Any points with noise, then denoise. That's actually the least square thing. Right. Well, also last time we told you, right? I mean, if we have a complete basis, I can do the rotation, right? If matrix A is a square, capital D is the same, right? Become a square matrix. I can do the power equation to the complete dictionary. Right? But sometimes, most of the time, that can also a little bit idealistic. Find a Fourier transform, wavelets, or whatever exists the basis, right? Rotate my data so that I make them sparse. So essentially, I'm in the same space. I try to just rotate the data, make them sparse, right? But sometimes the observation X, right, is the sparse structure may come from a much higher dimension space, right? DOD can be very high. Right? This is very tall. This is very fat matrix. Okay. I need a lot more dictionary columns. X is a sparse composition of those columns. Okay, A can be very fat. So Z is much higher dimension than X. So you have to lift X into a higher dimension space to see that low dimension structure. This is actually most common. So this is what we call, this is over-complete prediction. The square is complete. Whole matrix is under-determined, right? Under-complete. Right? PCS is an under-complete dictionary. Dictionary is complete. This is over-complete. So you get a general, right? We're going to powerful. More powerful family model. But it's harder to solve. For example, if I X actually I exist, I think such A exists, right? But the Z is k-sparse. So here, D is this direction. Capital D is this direction, right? Little d is much higher than capital D. Z is sparse. Z only selected k columns of A to do the combination, right? Get a picture? So this is less than equal to k. So this is the picture. This is how we call sparse autoencoding, right? You probably heard this. A lot of people are trying to do this. This is something people can learn from natural images. This is a very early work from neuroscience, learned from the human eyes, how many filters. Our eyes learn visual patterns, right? Well, our brain actually learned those sparse dictionaries. Right? In our brain, we interpolating all the edges into the world. So how do we solve this? Let's solve the easy part. The easy part we know how to do, right? If A is given, if I give you A is known, if I give you X observation, I can solve for X, Z. As I said, this is already considered before considered as NPR problem, right? Solving a sparse solution is already combinatorial. N choose K or little d choose K, right? Problem, right? In the extreme case. But turns out this can be solved by one more. 基本上是这个世纪的头10年大家在做这个事情啊，第二个10年大家在玩 deep networks， 对，头10年在玩这个啊。To do this. Turns out we know this is just do a possible gradient, right? You already learned that, right? Just compute the gradient and do the steps, okay? This is even the naive one, right? There's not the acceleration or anything. Absolutely fancy, I guess it's just stupid. Turns out even solving this problem, you can do acceleration, right? So the ESTA is the most basic one, okay, to solve this problem. Using acceleration, this can be solved much more efficiently. So you can solve this and doing using this ESTA, this iterative soft thresholding algorithm, right? Very simple. This is essentially gradient descent. Right? Now, the hard part is what if A is not known, right? This is what actually Yang Kun was interested. Actually, most people were already interested, right? Remember last lecture we spent my last lecture to spend on a complete A when A is a square matrix, okay? So we need to learn from many pairs of examples. Then what can do, right? I don't know A now, but I can observe, right? A is a black box to me, but I can give some sparsity, right? See what the output of X is, right? You have to give me something, right? A 是不知道，但是你可以告诉我，give me some sparse at Z, show me what the X looks like, right? 有输入和输出嘛，它是个 black box， but I should give me some sparse. 如果什么都没有，那我就 black box is black box, right? I don't know nothing about it. So the idea is give me some input output of this black box. So I hopefully I can see from X and Z from the pairs. I can learn A. Now how do you do that? Right? So now the idea is very simple, right? If I can think about the list. If I have X, if I know A, I know it's going through this process, this is going to decode Z, right? Because this is the ESTA algorithm. 对不对 ？Take iteration, another iteration, another iteration, 对不对 ？Take 足够 iteration, the output will be Z, 对不对？这不是前面这个算法告诉我的嘛，对不对？就 take enough number of iteration from 从 X 开始 ，take enough iteration, start a random Z, I should be able to converge to the correct state. 所以这个 pair 就是这是输入，这是输出嘛 ，right? This is an input and output of this process, right? Except Those I don't know this parameter now. I don't know A anymore, right? Those matrix I don't know anymore. 是不是？那怎么办呢？学呀，对吧？这是这输出对不对？这不就是一个 deep network 吗？那就该 deep networks end to end 有法。Right? Model the whole process, just F, right? Each layer to this step to here, right? It's exactly just the iteration of this type. Linear matrix hit plus some bias, right? And this is for linear operator plus some bias. And the linear thresholding to the next layer. It's deep networks. This is exactly what Yamato realized, right? It's eating it. So it's just X output goes through sequence. First iteration, second iteration, L iteration. If I lump all the theta as the W, right? W is S, I don't know, right? They are all unknown to me. I just learn those. Should give me output Z. So the output of this network should fit the parameters. Pair data. Should be an end-to-end network. This is exactly we call learned ISTA, right? 第一年那个时候神经网络还不在，他都不敢内训这像个神经网络 ，OK？ 如果他内训这像个神经网络，他的 paper 肯定被 rejected。2001年开始 ，OK？I'm not kidding. OK， 所以他说 this is the learned ISTA. To learn the ISTA. It's a sparse recovery. Because sparsity was very hot. If you mention sparsity, you cannot mention this is a neural network. OK？ Anyway， 所以有时候同学们你们知道一点 history 啊，还知道对吧？这个也是其实比较 ridiculous 的啊，不像你们所看到的和想到的这样。No, let's make this more general, right? This is exactly what it is, right? Look at this. This is exactly right within the classification, right? So now we can make this more general. We have pair of data, input X, Y. Y can now could be general, right? Could be right. The output there could be loss function. If it's classification, Y could be a label for X. X could be an image. Y could be a label. Again, that's input. Goes for deep networks. Output the label. Right? The S-way label, output from the network, and output Y. Then the loss function may be a cross entropy, right? Or if it's a signal, I use quadratic, mixed square fitting, right? Cross entropy or mixed square, or minimal mean square error. Or the blocks could be residual blocks, general.后面ISTA is the residual block. Which one? 谁像谁自己去决定啊 ？Who is 谁在模仿谁？大家去想。Of course, you can have the flat or linear or soft mask. Right. Thresholding. Later we'll see why we're doing thresholding. Right. PCA is doing that. Well, because thresholding is precisely making things sparse. It's actually getting rid of noise. It's actually compression. Okay. We'll actually go through that later. More systematically, right? Now you just have to assume. That's exactly what it does, right? So the next question is how do we compute the gradient, right? Now this is a general class problem. We know it's a concatenation of many layers, but the rest I have to compute the star gradient against the theta. That's easy, just compute the gradient, right? Partial f, partial theta, right? Turns out, well, because this is not a right. How do we compute the gradient, right? If I have a function, I just do the gradient, right? DL3 d theta is the gradient. Everybody knows this, right? 概念上很简单，就是求导数嘛，就西塔求导数，对不对 ？This is the one we do all the time, right? This is scalar, this is Rn, and dimensional. This is just a little bit complicated, right? 你说是矩阵或者是这个向量啊，就是这个。Right? That's a little bit complicated. Right? It's 矩阵乘啊，这是矩阵乘向量 ，right? 对，这叫微分形式啊，就是这个是一个 notation，实际上跟我们做的 calculus partial L partial theta 是一模一样，哎，只是写成这个形式呢 is more general， 就相当于把这个方程 L 啊，相当于是它一阶导数展开， 你可以把它看成一个小的变量，对不对 ？Up to first order optimization to this original function， 就是 Taylor expression respect to each of the variable。Right, this is a small wave 啊，用这个符号。实际上，这个符号是最早是拿个离子，最早是用这个符号啊。后来大家在下车这里回去了，实际上用了一个不太好的这种符号，实际上是更加 general 啊。甚至the function can be a theta or beta. They just do expression partial L to theta and d theta, partial L partial beta 加上 partial L partial beta d beta， 所以你可以全部就省线性展开，知道吗？ This is actually more general符号。If you get used to this, it's the more systematic. Okay, more general. Okay. If you get used to this, it's actually easier to do back propagation. Fine. That's why in the appendix we start using adopt this new framework. Right. So now, of course, everybody knows this, right? You learn from calculus, 对吧？大家都知道多变量微分积分，对吧？多变量微分，对吧？ Calculus, multivariable calculus, everybody knows how to do this. But turns out this L has a lot of structure, right? Remember, it's a concatenation. Right? So this L is actually, we know the function L looks like this, right? If L has even this full function concatenated, you can see when we compute the gradient with respect to theta, right? And so it's only we first do the derivative f against the g, then g against theta. Let's just have to multiply them together， 对不对？这两个矩阵乘在一起就行了，是不是？所以看分步骤。We can compute this. This has nothing to do with this derivative. And compute this, it has nothing to do with that one. Right? They can be computed separately. And then multiply together. 所以自然计算知道怎么嵌入，对不对？我给大家嵌入啊。多变量函数稍微复杂一点，因为变成一个矩阵啊，变成一个矩阵啊，乘一下。Jacobi， 它这就是 Jacobi 矩阵，对吧？ 乘上这一套啊，打开它就是在后面 gradient 啊。So now how do we do this? Well, now this is only two composition. Of course, the deep network has many combination, right? How do we do it? Right, simple. It's this chain rule. It's a little bit 长, right? A little bit longer than usual. That's it. So now let's look back, right? So if I have the network, right? This is the input, embedding usually, right? So normally, especially now we're already in the token business, right? Imagine some image and do some embedding. This is already this is only this after initialization, preparing the data, 所以来做 tokenization， 对不对？各种 embedding 啊，我把这个数据不需要打成模块啊，各种声音也是，或者语言，对不对？语言先做这个 embedding 啊。 Pre-train the model and embedding, prepare yourself. Then send it to a network. This could be a residual network, residual block. This could be a res network. This could be a East block. Okay? Anything from optimization. This block may have something to do with your trying to optimize. We'll talk about that later. Okay? 就是这个结构啊，这个 F 肯定是跟你的优化程度有关。待会儿我们后面会专门讲这件事情，对吧？这个 F 该是什么比重先不管，对吧？ 反正是一个 layer, some iteration, right? Some iteration, just like East time. You know, if you don't like it, right, you always think about East time, okay? 就考虑这个特殊情况就行了啊。Then we repeat multiple times, right? L 乘 compose, 对吧 ？F L， 然后输出 ，right？ 到 L 乘，最后做 classification 嘛，最后一层这边往有一个尾巴 ，right？ 到我要做 classification 嘛，我要做 regression 嘛，我 predict 那个 next world 嘛，对不对？做什么 soft threshold 嘛，对不对？一般就干这个事儿嘛，对不对？就是最后一层嘛。Then there's some loss function. Is this classification good enough? Right after doing soft thresholding, right? This cross entropy, or this is the prediction next word, right? Very simple, right? This is as general as gets. Not necessarily function. No, it's just doing it, right? I want this one to compute all the way against this guy, right? Or every layer there's a theta. Okay, then let's do the computation, right? Every layer there are two variables, right? There's a theta, there's a z. Z depends on the previous theta, right? All the children theta, right? ZL depends on all the previous layers, all the thetas in the previous layers, right? So 所以我就 differentiate 数就好了，所以我就把 gradient against the last layer, L against this one, 对吧？ partial L, partial ZL. Well, F against the partial Z. And then the next time I want to compute against this guy, right? For example, I want to compute with the ZL. Right? Then that's just the partial against the Z. Remember, ZL plus 1 is equal to FL ZL, right? Capital L. Right, it's just this guy. Compute the df L, and then this one is already computed here, right? This is already partial L, partial X, ZL plus 1. Then this is just the ZL1 against the ZL. Okay? ZL plus 1 against the ZL. 给它求到，给它存起来，是吧？但我在求这个时候 when I do this differentiation, this one is already computed. I can just borrow from left. 对不对 ？I will have to compute this guy. 是不是？对的，我在这一层求微分，跟上一层是不相关的。上一层已经求过这个，所以你可以发现，我再往下面，再往前面层 ，if I do further to the layer, each layer I only have to compute in one new differential. All the red one has already been computed in the past. 对不对？ If you want this one is already computed. The theta is theta L. This one is already computed. If I want to compute it to all the way to Z1, right? Partial L, partial Z2 is already computed in the previous layer. So every layer, I only have to differentiate against the new variable arise in that particular layer. Because all the derivative in the past has been computed. 对不对？都可以 borrow 直接乘过去就好。So every layer you only have to differentiate against the variables in that layer. And all the parent layer has already been computed. Right? You do the same backward. Right? 所以这个很简单吧，对吧？那这就是切入，对不对？跟这个 surface generalization of this, when computing dL to d theta, right? Up to G, I only have to compute because this one is already computed, the partial and partial G is already computed in the previous layer. 知道吗？已经 pre-computed by that one. So you just repeat the chain rule. So once you sort it out, and of course, these days, you don't even need to do this, right? You can go to Hugging Face tunnel, right? This is how do you compute the partial derivatives, right? But that's really bad, guys, right? What's the danger of use what the algorithms do? 就跟我刚才讲的一样，200年，大家都同一个 idea. You never get a chance to change it if you don't understand what's going on. Okay? Oh, because everybody's using this, right? Everybody thinks this is right. Really? You cannot do any better. Are you sure? So if you understand what's going on, you actually can change things, right? But for now, let's assume this is the best you can do. Okay? So let's do some example, right? It's just a simple example. A very simple scalar two-layer network, right? Just get the idea. The first layer has an input. We head with some parameter linear operator. It's kind of resemble the general structure, right? That was very simple. You head with some linear expression, sigma. Let's say that's a source of specialty. Then you head with the output of Z1, you head with another theta, right? Try to predict this is some linear regression. Right. The second layer, let's give you Z2. Z2, suppose that's linear regression, you try to regress Y. Right? Using the output of some nonlinear, one layer nonlinear network, you try to regress some function Y. Okay? It's a very simple model. It's everything scalar. Okay? But Sense has this. Then what do you do? So you can see the whole input, right? First, go to Z1, first layer, and Z2 is second layer, and the loss function. 是吧？很简单，就2层啊 ，two-layer network. You know how we compute? Well, first, against Z2, right? L against Z2. Well, let's see where we can do this. You write down partial dl dz. And if you to go to because dl dz 就这个，是吧？就 differential 嘛。Then you can do the Taylor expansion for Z2. Z2 looks like this, right? Z2 looks like this. So just a partial Z2, partial sigma 2, partial Z1, 就是 Z1 D2。你看，你把它写成 up to first order 线性展开，就像这个样子。只要这就是泰勒展开，对不对？这是泰勒展开 ，nothing， 而且是 up to first order， 哎 ，very simple， you learn this。那在这第 sigma one 的 Z1 against the variable， 在它这一层只有 sigma one 和 x， 对，但 variable 只有 sigma one， 所以这样。It looks like that, right? It's not one， 首先有 sigma， right？ 所以就 partial sigma 对里面所有球微分，然后再乘上里面进去嵌入，对不对？再给 sigma one 求导 x 出来了，对不对？这也是个小嵌入，在这里，而 everything is 嵌入。Now, so why does it save you? Right? So when you're computing backwards, this is the forward. See, forward network like this, x goes to this. Backward computing like this, right? So now you can see how this actually help you. Is that if I want to extract gradient, I want to find gradient partial L, partial theta, because that's what I want to really descend on theta. Okay? Theta 1, theta 2 are I want to optimize. I want to compute those gradient, right? How do you track them? See, all the red line is when you compute the first layer, right? Blue line is to compute the second layer, right? Oh, sorry, yeah. This is loss function. Right? First line is only the loss function. The second layer is the blue line is the second layer, first layer, second layer. The brown line is the first layer, right? We're going backwards. 所以你看，我在从头到尾，对吧？Differential against theta 2. I only need to. This is only from the loss function. So all the ones I borrow from the previous layer, I can repeatedly use that. Recycle that. Okay, hoping later, if I want to compute against theta, you rely on a later layer. Always, those things are already computed before. Imagine the chain is very long. You can recycle a lot of them, right? So that's why you save a lot. You have to really compute. You don't have to compute theta 1 completely independently from backward. Right? Just borrow whatever you have computed. To the past to theta 1 all the way. Get it? 啊，这明白吗？所以这个是大家明白这个道理。说白了就是嵌入 ，OK？ 对于这种 past optimization 嵌入。And backward propagation， 虽然现在大家都知道好像是对吧 ？The name he didn't give the name backward propagation， but the idea has been invented a long time ago。自由控制optimal control，optimal path optimization。People saw 专门有一些 thesis 62年 thesis， 实际上在那个像贝尔赞的 thesis 里面也有这个 idea， 这是他没有去把它系统化。1962那个就是作为自由控制optimal control people has already done this at least 20 years before. Whenever you have this concatenation function composition, you always compute it within the back propagation. It's a very natural architecture if you have path optimization. 就像 solve game 一样，整一步、两步、三步、四步，最后看每一步都有不同的 option. You try to optimize the sequence of optimal segment. So that's exactly optimal control. 所以现在是 VLA 的给干这事儿，对不对 ？Reinforced learning 还在干这事儿，按 optimal path。AlphaGo 还在干这个。Reinforced learning 在干这事儿，还在 define the optimal path and options every steps so that they define segments. That's exactly doing this. Every step you find optimal theta. Theta is a control actually in a different setting. So that's actually the history. So you have to know. See, you don't have to a lot of things, right? Later, if you really know, have learned very solid, rigorous system, systematic approach to certain things, you don't have to reinvent. You have to spend a lot of time to try and error, to reinvent this, or to even rename them, right? So actually rename, what is a scholarship? Scholarship is actually the ability to recognize what is new, what is not new, okay? That's the first step. If you don't have scholarship, you cannot recognize something's new, then you just always rename it. Actually, that's called adding noise. 我现在我知道告诉你吧 ，intelligence is about denoising, right? Get rid of noise, get rid of reduce entropy. But if your name something is already there with a different name that you're adding noise, okay, it's anti-intelligence. 想清楚这个问题啊。到底是想做这个世界的 diffuser 还是 denoiser? Okay, that's the difference. So you have to decide, right? You want to reduce the world's entropy, as actually want to increase the entropy of the world. That's up to you. So any question about this part? As I said, although this is not an optimization course, but everything about the course relies on. As I said, computing is all. So this is a great time for you to pick up. If you are not so familiar with optimization, now this is your time to catch up, right? There's material, reading material, giving the references, read them. Right. As you can see, almost every book I wrote has optimization equipment already goes to division. But although every book uses different aspect of optimization, okay? The previous book has more general introduction about the optimization condition. If you have gone back, it's time for you to catch up. Okay, general story. Although this lecture help you to warm up a little bit, give you a little bit of overview of history of optimization and the key ideas. As I said, there are not that many great ideas. Okay, although there may be tens of thousands of papers. That's it. There's probably only 5 names you need to remember. Okay, probably 4 or 5 good ideas. Right. All paper is just recycling or to fine tune. And this book, of course, we pick the presentation in this book is more tailored to deep learning, right? The general nonlinear optimization problem, and also the chain rule, which is important to training neural networks, right? And the location that can help you to unify. Not only chain rule. In terms of chain rule, doesn't have not only apply to when you have this sequence of composition, but maybe also there's a lot of functions maybe you have a hierarchical structure. You'll find out, right? The chain rule, this actually idea is actually very, very powerful. If you have a graph structure of your variables, some function has the variables has natural hierarchical structure, right? Not just the concatenation, right? You can also use this kind of application, compute very efficiently, right? So that's why we introduced the more general notation, the differential notation, right? Rather than the typical calculus gradient notation, because that's also sort of limited. If you deal with one variable at a time, it's okay. But when you're dealing with a sequence of variables, it's actually a little bit limited, right? So here, remember, each layer we are dealing with at least 2 variables. Well, one is the state, z, another one is theta, the variables, right? The parameter of the network. So that's why you need a better notation. You need to use this kind of notation. Okay, it's better. It's just a notation. Get used to it, right? It's not that scary. So any questions about? So this is supposed to be a warm-up lecture for optimization, but also sort of help you to see the connection between optimization and the architecture of deep networks. Okay. So what time is it? 2:30. Let's take a break. 5 minutes break. Bar break. Perfect. Get to the next. We're taking a 5 minutes break.